Hello, welcome to Notable Nobels, a podcast about the Nobel Prizes in Physiology or Medicine. My name is Harrison Doolin. I am a PhD candidate at the University of California, Riverside, and I will be your host for this web series. The purpose of this series is to trace key advancements made in the biological and medical sciences over the past 120 years or so, and we're using the Nobel Prizes in Physiology or Medicine as a guide. Now, every career has its highest prize. The highest prize for an athlete is an Olympic gold medal, and it's been awesome watching everyone compete in Tokyo over the last couple of weeks. But for a scientist, the highest prize is the Nobel Prize. It's the most prestigious award a scientist can receive, and it marks discoveries that have made a profound impact on our understanding of biology and our ability to treat diseases. Today's episode is the third of a three-part series looking at Nobel Prizes awarded for the discovery of antibiotics, one of the most important discoveries in the history of medicine. We'll be examining the 1952 Nobel Prize in Physiology or Medicine, which was awarded to Selman Waksman. The Nobel Assembly at the Karolinska Institute chose to give Waksman the award, quote, for his discovery of Streptomycin, the first antibiotic effective against tuberculosis, unquote. We'll be going over how Waksman's lab isolated streptomycin from a common soil bacterium, how streptomycin and other antibiotics kill bacteria, and we'll talk about the growing problem of antibiotic resistance. But first, a little bit of background on Waksman. Waksman was born in 1888 in Ukraine. He attended school in Odessa before immigrating to the United States in 1910. He attended Rutgers University in New Jersey, graduating with a Bachelor of Science degree in agriculture in 1915. Waksman stayed on at the university to do a master's degree, working as a research assistant to Dr. Jacob Lippmann, where he focused his study on soil microorganisms. He then moved briefly to California, where he earned a PhD in biochemistry in 1918 from UC Berkeley. Then he returned to Rutgers to join the faculty of the Department of Biochemistry and Microbiology. He would spend the rest of his career at Rutgers, and it was there that he would make his Nobel Prize-winning discovery, the discovery of an antibiotic effective against tuberculosis. So what was the big deal about tuberculosis back in Waksman's day? Well, it was an extremely widespread killer responsible for millions of deaths each year. The cause of the disease was determined to be a bacterium called Mycobacterium tuberculosis, a discovery that had been made by Robert Koch in 1882 that would earn Koch his Nobel Prize in Physiology or Medicine. The disease typically begins when the tuberculosis bacteria infect a person's lungs. Once inside the lungs, the bacteria infect special cells of the innate immune system called macrophages. Macrophages are like ground troops for the innate immune system, and they are normally very good at eliminating invading bacteria. However, they are unable to kill Mycobacterium tuberculosis. The bacteria take advantage of this, and they set up an infection inside the macrophages. The bacteria can lie dormant for a very long time, sometimes years, and in most cases, a person is infected for life unless they receive treatment. As the bacteria replicate and spread throughout the lung tissue becomes damaged. The person will have trouble breathing and will begin coughing up blood. If the infection manages to spread beyond the lungs, the bacteria can invade other organs, which can lead to widespread organ damage. If left untreated, damage to the lungs and other organs will eventually be fatal. Unfortunately, back in Waksman's day, the options for treating infected tuberculosis patients were few. However, Koch's discovery that tuberculosis disease was an airborne bacterial infection informed how public health measures could combat the disease. Cities began implementing sanitation standards, and people in the active contagious stage of the disease could be quarantined at special sanatoriums. Additionally, Koch's discovery allowed scientists to work with the bacteria in the lab, and many scientists began working on a vaccine against the pathogen. And their efforts were not without result. In 1921, an important breakthrough was made in the fight against tuberculosis with the development of a vaccine called the BCG vaccine, which is still in use today. This vaccine had taken scientists at the Pasteur Institute in France 13 years to develop. They started by growing the isolated tuberculosis bacterium in their lab. They were growing the bacterium in a special media containing glycine, potatoes, and bull bile. I don't know how they arrived at that combination of ingredients, but that's where they landed. They noticed that tuberculosis bacteria grown in this media seemed to make animals less sick. They wondered if continuing to grow the bacteria in this special bile glycine potato medium might change the bacteria to the point where it would no longer cause disease in humans, which would make it a good vaccine candidate. By 1921, they had isolated the BCG strain of tuberculosis that failed to cause disease in animals. They were ready to begin human trials with this new BCG vaccine. Administration of the BCG vaccine to infants in France seemed to have no side effects, and the French scientists reported a decrease in cases of tuberculosis among vaccinated children. Things seemed to be going well, but scientists in other countries raised doubts about the effectiveness of the vaccine. Then in 1930, disaster struck. In the German city of Lübeck, BCG tuberculosis was sent to a local tuberculosis scientist for culture and eventual use for vaccination. The scientist who received the BCG vaccine strain took it back to his lab, where he began culturing the bacteria in the same lab where he was culturing dangerous, deadly strains of tuberculosis. The scientist took the BCG strain that he had cultured and used it to vaccinate 250 children. The result was that 208 of those children got sick with tuberculosis and 73 of them died. An investigation was immediately initiated by the German government to determine what had happened. About 2 years later, the investigation concluded that the BCG strain had become contaminated in the lab with a dangerous strain of tuberculosis. They concluded the BCG strain remained safe to give to people, but by that point, the damage had been done. Once people got wind of the Lübeck disaster, confidence in the BCG vaccine evaporated, and for the next decade, little progress was made in vaccinating people against tuberculosis. It was around this point that people's attention began to shift from vaccines for tuberculosis to antibiotics. Antibiotics were originally envisioned by the scientist Paul Ehrlich, who imagined quote-unquote magic bullet compounds that would be able to selectively target bacteria without harming the host. By the 1930s, the first major class of antibiotics were in use, the sulfa drugs. Then in the beginning of the 1940s, penicillin's proven effectiveness as a wonder drug further spurred interest in antibiotics. However, both the sulfa drugs and the penicillins proved ineffective against tuberculosis. The hunt was on for an antibiotic that could work against this particularly widespread, deadly killer. This brings us back to Waksman. Waksman had spent most of his scientific career working in agriculture. His main area of expertise was in soil microorganisms. This isn't an area of study one would expect to have a big impact on the medical field. However, Waksman began working with a family of common soil bacteria called actinomycetes. These organisms had originally been studied for their role in decomposition, but it had also been discovered that certain members of this family of bacteria could inhibit the growth of other bacteria as well as fungi. This property of the actinomycetes to block the growth of other microbes was the same property that had attracted Alexander Fleming to the mold that made penicillin. Here's a quote from Waksman's Nobel lecture explaining how he began his research. Quote, "It was the knowledge of the great abundance and wide distribution of the actinomycetes, which dated back nearly 3 decades, and the recognition of the marked activity of this group of organisms against other organisms that led me in 1939 to undertake a systematic study of their ability to produce antibiotics." Unquote. In 1940, Waksman Lab was able to isolate a substance from a member of the actinomycetes family that was very effective at inhibiting the growth of other microbes in culture. They called this substance actinomycin. However, actinomycin proved to be extremely toxic when given to test animals, which ruled out its use as an antibiotic. Remember from last time, it's not enough that an antibiotic can kill or inhibit the growth of bacteria. For the antibiotic to be useful, it also must not be toxic to the host. So the search continued. Waksman's lab isolated another potential antibiotic in 1942 called streptomycin, but it too proved to be too toxic in animals. However, it wasn't as toxic as actinomycin, so Waksman's lab began to screen for substances that were chemically similar to streptomycin, hoping to find one that was safe enough to use as an antibiotic. In September of 1943, they found one. Waksman's research assistant Albert Schatz isolated a new antibiotic from actinomycetes bacteria, and they called this new substance streptomycin. What was particularly exciting about this new antibiotic was its effectiveness against tuberculosis. The drug was tested in a guinea pig model of tuberculosis, and here's what Waksman had to say about the results. Quote, "The conclusion was reached that streptomycin is the most effective tuberculochemotherapeutic agent so far studied. Its relatively low toxicity for guinea pigs, its high efficacy in resolving and suppressing what would otherwise be lethal tuberculosis, established streptomycin as a drug worthy of serious consideration for the treatment of tuberculosis." Unquote. And so, they moved forward with testing the drug in human tuberculosis patients. They didn't go about testing it in a randomized, controlled clinical trial like we would do today. The drug was used on a case-by-case basis in the United States. The results of the first 100 patients given the drug were encouraging, though, enough to eventually start a clinical trial. In the U.S., a randomized clinical trial enrolling 541 patients divided evenly into two groups was finished in 1950. The result was an approximately 50% decrease in tuberculosis deaths among patients given streptomycin compared to the control group. This was clear evidence that streptomycin was the best antibiotic available for curing tuberculosis. Use of the drug spread around the world, and in 1952, Waksman was awarded the Nobel Prize in Physiology or Medicine. Waksman remained at Rutgers University until he retired in 1958, and his lab continued to isolate many more antibiotics from soil microorganisms. The effect streptomycin had on medical history was exceptional. While much progress has been made in preventing tuberculosis with vaccines and public health measures, streptomycin gave physicians a way to cure infected patients. The new antibiotic became a helpful tool to bring down tuberculosis deaths and curb the spread of the disease. These days, though tuberculosis remains a global threat with an estimated 1.4 million deaths reported each year, cases of the disease are restricted to countries that lack access to proper sanitation, vaccines, and antibiotics. The United States currently enjoys one of the lowest tuberculosis rates in the world, so low that we don't use the BCG vaccine, and the annual number of new tuberculosis cases has been falling steadily over the past 70 years. Antibiotics are the main treatment used to cure tuberculosis patients, though streptomycin is no longer the first-line treatment. Even back in Waksman's day, it was noted that streptomycin had the unfortunate side effect of sometimes causing permanent deafness, which is obviously a very serious side effect. Additionally, there is a growing problem of antibiotic-resistant strains of Mycobacterium tuberculosis. Streptomycin-resistant strains of tuberculosis were noticed even before Waksman got his Nobel Prize. Waksman's lab noticed that cultures of tuberculosis given streptomycin would quickly develop resistance to the antibiotic. This led Waksman to make the following comment during his Nobel lecture, quote, "The problem of variation in sensitivity of different strains of the same organism to streptomycin and the increasing resistance of the bacteria on prolonged contact with it are of considerable theoretical and practical importance." Unquote. The threat of antibiotic resistance has not gotten smaller since Waksman's day. The World Health Organization has listed antibiotic resistance as one of the biggest threats to global health in the coming decade. since it is such a pressing issue, I'd like to take some time to go over how bacteria can develop resistance to antibiotics. To better understand how this works, though, we first need to go over the many ways antibiotics attack and kill bacteria. Now remember, what makes antibiotics so good is their ability to target the bacteria cells while leaving the host cells alone. This means that the best antibiotics target molecules or molecular pathways that are found in bacteria but not in human cells. We already mentioned one of these molecules in the episode about penicillin. Penicillin belongs to a family of antibiotics called beta-lactams, and these all have the same mechanism of action. Beta-lactams block the synthesis of bacteria cell walls. They do this by targeting a molecule called peptidoglycan that is a critical component of the bacteria cell wall. Since mammalian cells do not have a cell wall, beta-lactams can specifically target and kill the bacteria cells while not harming the human cells. But cell walls aren't the only target antibiotics can choose. Antibiotics can also target bacteria metabolic pathways. Metabolic pathways involve the production of a specific chemical for a cell to use. For example, bacteria have enzymes that are used to synthesize a molecule called folate, also called vitamin B9. Folate is a necessary vitamin used in DNA and RNA synthesis by both animal cells and bacteria cells. However, while bacteria synthesize their own folate, humans don't. We get our vitamin B9 from our diet. This means folate synthesis only happens in the bacteria, and so it can be targeted by antibiotics without affecting the human cells. The class of antibiotics that target the folate metabolic pathway are the sulfa drugs, which we talked about previously on this podcast. Now, while it makes sense that antibiotics would target things like cell walls and folate synthesis, which have no homologs in mammalian cells, other antibiotics target things like protein and nucleic acid synthesis. At first glance, this may seem puzzling since all cells, both bacterial and mammalian, must synthesize proteins and nucleic acids to survive and replicate. Nevertheless, these pathways can be targeted by antibiotics. For example, streptomycin works by blocking protein synthesis in bacteria cells. So the question becomes, how can these antibiotics target these pathways specifically in the bacteria, but not the host? How can streptomycin block bacteria protein synthesis, but not mammalian protein synthesis? The answer to that question is that bacteria and mammalian cells use different machinery to do the same thing. The molecules that synthesize proteins in bacteria are sufficiently different from the molecules that synthesize proteins in mammalian cells that they can be targeted by the antibiotics. Similarly, bacteria use enzymes to synthesize nucleic acids, and these enzymes are different enough from the mammalian enzymes so that the antibiotics can distinguish between the two systems and only target the bacteria. Here's a rather silly way to think about it. Imagine you work as a secret agent for the government, and you have been tasked with assassinating a member of a militant group hostile to your country. You are told that the target works in a factory, but that this factory is important for producing spy gear for your agency. Now, the information that the target works in the factory is by itself not going to be enough to help you find your target. Now, one way to take out the target would be to blow up the factory. But since your agency needs the factory to make spy gear for them, you realize you're going to need a more specific approach. Fortunately, your orders also include the information that the target works on the assembly line. This is good. This is more specific. It rules out delivery drivers and upper management, but there will still be lots of other people on the assembly line who will be doing the same job as the target, and you don't want to take out those other people. So how can you specifically target the militant? Fortunately, again, your orders tell you that the target will be wearing a pink shirt, brown pants, and yellow sneakers. This information makes the target look different enough from the other workers that you can specifically snipe him from your perch across the street. Now, as you might have guessed, the sniper is like the antibiotic. Just like the appearance of the sniper's target is different enough from the surrounding workers, the bacteria molecules look sufficiently different from the surrounding mammalian molecules that they can be targeted by the antibiotics even if those molecules do the same task inside the cell. Now that we have a more molecular understanding of how the antibiotics work, let's talk a bit about how bacteria can develop resistance to antibiotics. One of the more straightforward ways bacteria can be resistant to antibiotic treatment is to prevent the antibiotic from getting inside the bacteria cell. Some bacteria do this by infecting the cells of their host. So they'll hide out inside the infected cell, and that infected cell will sort of act as a barrier to prevent the bacteria from coming into contact with antimicrobial compounds. Other bacteria will build their own barriers, and these are called biofilms. The bacteria can hide out in these slime-like biofilm structures, which can block antibiotics from reaching the bacteria. If the antibiotic should still manage to enter the bacteria cell, a second way bacteria can resist antibiotics is by kicking the antibiotic back out again. Bacteria have many different types of secretory systems and efflux pumps that can remove the antibiotic should it end up inside the bacteria. A third way bacteria can resist antibiotics is by chemically modifying the antibiotic so that it can no longer do its job. An example of this are the beta-lactamases, which can inactivate the beta-lactam antibiotics, including penicillin. The beta-lactamases chemically alter the penicillin so that it can no longer bind to its target molecule, which allows the bacteria to grow even in the presence of the penicillin. Bacteria that have these enzymes, or other genes that confer resistance, can give these genes to their progeny and can also give these genes to neighboring bacteria in a process called horizontal gene transfer. The result is that resistance genes can be passed around a colony of bacteria and allow for rapid development of resistance to antibiotics. The fourth way bacteria can develop resistance to antibiotics is the more traditional way people think about resistance. Rather than chemically modifying the antibiotic, the bacteria can also evolve chemical changes in the target molecule that the antibiotic is designed to attack. This change will be such that the antibiotic can no longer recognize the molecule it's supposed to attack. So let's go back to our sniper example. Let's suppose that the sniper is on the lookout for the assembly line worker in the pink shirt, brown pants, and yellow sneakers. But suppose the target changes their clothes and shows up to work with a blue shirt instead of a pink shirt. The sniper wouldn't shoot the target now. So this is sort of what happens when the bacteria mutate. If the bacteria have a mutant protein that the antibiotic can no longer recognize, the antibiotic won't work anymore. In light of all these ways bacteria can resist antibiotic treatment, there are a few different practices doctors use to prevent the spread of antibiotic resistance. One of the easiest methods is to only use antibiotics when needed. If you have a light infection that can be cured with bed rest and fluids and isn't too serious, antibiotics may not be necessary. However, if antibiotics are given, then it is important that you take the full course of antibiotics, even if you start to feel better, since you don't want to give the resistant bacteria a chance to spread the resistance to any leftover susceptible bacteria. Another practice is to sequence the DNA of the bacteria infecting a patient to check for known mutations that confer antibiotic resistance. This allows the doctor to prescribe antibiotics that will have a better shot at clearing the infection. There's no point in giving the antibiotic if you know the bacteria is resistant to it, right? Finally, a common practice is to give different classes of antibiotics simultaneously, and specifically to use antibiotics that work by different mechanisms. For example, a common treatment for tuberculosis is to take the antibiotics rifampin and isoniazid together. Now, rifampin works by blocking bacteria RNA synthesis, while isoniazid works by a completely different mechanism, blocking bacteria's cell wall synthesis. The logic is that even if the bacteria develop resistance to one of these antibiotics, they will still be susceptible to the other, so you can still clear the bacteria and prevent the spread of resistant strains. Now, all these practices together may help curb the spread of antibiotic resistance, but unfortunately, antibiotic resistance is still spreading. Strains of tuberculosis called extensively drug-resistant TB have been isolated around the world, and these strains are almost untreatable at this point. So more research is needed to find new strategies that can target these resistant strains and to prevent their spread. However, in the meantime, antibiotics remain one of the most amazing discoveries in the history of medicine. They continue to save millions and millions of lives every year, and they remain one of our best weapons in our fight against bacterial diseases. So that concludes this 11th episode of Notable Nobels. This episode was recorded on August 15th, 2021. I want to thank Digital Mind Productions for providing the music. Next time on Notable Nobels, we will be discussing an extremely controversial chemical that, while having an amazing benefit for human health, would also help spark the modern environmentalist movement and the creation of the United States Environmental Protection Agency. So what was that chemical? Well, listen next time to find out. Thanks so much for listening. We'll see you then.